For years, we've treated kernel security like building a fortress. We've poured all of our energy into reinforcing the main gate, that CPU kernel boundary. But what if the deadliest attack doesn't bother with the front door at all? What if it comes from a trusted ally already inside the walls? Well, today we're diving into exactly that. We're talking about the GPU and a wild technique called PhantomMap that turns the driver's own logic into a master key for physical memory. All right, here's our game plan. We'll start by looking at a huge blind spot in how we think about CPU security. Then we'll break down the two critical design flaws that make this whole thing possible. After that, we'll see how attackers forge these flaws into a ghost key, show how it unlocks basically every door, and finally talk about a pretty slick and lightweight way to fix it. So let's set the stage. Our modern operating systems are kernels. They're supposed to be these digital fortresses, right? Completely impenetrable. And honestly, if you're only looking from the CPU's perspective, they pretty much are. I mean, you've got defenses like KSLR, which shuffles memory around, control flow integrity, or CFI, and privileged access never, PAN. All of these have made old-school attacks like code injection a total nightmare. The front door is locked, barred, and has a guard standing in front of it. But here's the crucial disconnect. All that armor, all that attention is laser-focused on the CPU. Meanwhile, we've got the GPU sitting right there, a super powerful coprocessor with its own way of managing memory and, importantly, direct memory access. Its driver has these incredibly deep, privileged hooks into physical memory, and that creates this massive blind spot that we've just kind of ignored. So how does this actually work? Well, PhantomMap isn't some kind of black magic. It works by exploiting two really fundamental and frankly lethal design flaws in the ARM Mali GPU driver. The first flaw is a concept the researchers call decoupled operations. See, when your app needs GPU memory, the driver does two things. First, it allocates the physical pages of memory. Then, in a completely separate, later step, it updates the GPU's page tables to map those pages. That gap, that separation between allocation and mapping, that creates a window of opportunity. This really puts it into perspective. On the CPU, when there's a page fault, the memory allocation and the mapping happen together. It's an atomic operation. Boom, done. There's zero time for an attacker to jump in. But the Mali driver, it's a two-step dance. An attacker can start the dance, and then, in that little pause before the second step, they can race the driver and mess with the outcome. The second lethal sin is all about misplaced trust. The Mali driver, when it gets certain requests, simply doesn't check what it's being asked to map. It just assumes that any physical address it's given is a legitimate GPU-owned page. It never bothers to actually verify the ownership or the type of that page. And you can literally see this when you look at the code. On the left, there's the CPU's page fault handler. See that? It's explicitly calling validation routines, checking page types, doing its homework before it creates a mapping. Now look at the right, the GPU driver's equivalent code path. It's empty. There's nothing. It just blindly trusts the physical address it was handed and maps it. Okay, so we've got a time window and a driver that's way too trusting. Now for the really cool part, how do attackers combine these to forge PhantomMap? See, they don't have to pick the kernel's locks. They just trick the kernel into redrawing its own floor plan, putting the most secret rooms right into the attacker's hands. The attack is just beautifully precise. First, the attacker makes a normal request for GPU memory. Then, in that time window we talked about, they use a completely separate and maybe even low-severity heap bug to corrupt the data structure that holds the physical addresses for that new memory. They swap out the real addresses with the physical addresses of whatever they want to target, say a kernel page table. Then they trigger the second, legitimate step of the mapping process. The driver, because it doesn't check, just reads the corrupted info and dutifully maps protected kernel memory right into the attacker's user space with right permissions. And that's really the heart of it. This isn't about finding some new bug in the mapping code itself. It's about hijacking the driver's normal, everyday workflow by feeding it bad data that it was never designed to second guess. So how powerful is this ghost key really? Is this just a cool theory for a paper? Oh, not at all. Let's look at what this does to fully patched modern devices out in the real world. Using a custom-built static analyzer, the researchers found not one, not two, but 15 distinct end-to-end exploit chains across different Mali architectures. This isn't just some one-off coding mistake. This is a systemic, architectural problem. This is where it gets just devastating. PhantomMap essentially walks right past the entire modern security stack. KSLR? Defeated. You can just map and read the kernel's physical page tables to find out where everything is. CFI? Bypassed. This is a data-only attack. You're not messing with control flow, you're just rewriting data. And maybe most importantly, PAN and SMAP? They don't matter. The memory writes come from the GPU, not the CPU, so the CPU's access control rules just don't apply. What PhantomMap really does is act as a vulnerability amplifier. It can take a pretty modest, maybe even unexploitable heap corruption bug and turn it into the absolute holy grail of kernel exploitation, a stable, reliable, arbitrary physical read-write primitive. And the practical results really speak for themselves. This technique was used to build the first known public exploit for a CVE that was previously thought to be too hard to use. In another case, it took an unreliable exploit that worked less than half the time and cranked its success rate up to a stable 90%. All right, so a flaw this deep in the architecture must require some massive, painful redesign to fix, right? Well, thankfully, the solution is surprisingly straightforward and, well, elegant. The fix they came up with gets right to the heart of that missing validation problem. It's a simple tag and check system. So when the driver allocates a physical page, it tags it, saying, hey, this page belongs to the GPU. Then, before it maps any page, it does a quick check. Does this page have my tag? If an attacker has swapped in a kernel page, the tag won't be there, and the whole operation gets shut down safely. And here's the best part. This fix, which completely shuts down the vulnerability at its root, has almost no impact on performance. We're talking less than a single percentage point of overhead on modern phones. It's a total no-brainer to implement. So this research leaves us with a really critical and kind of scary final question. We've just locked down the GPU's access to memory. But what about all the other powerful DMA-capable chips in a modern device? Your image signal processor, your neural processing unit, do their drivers have the same architectural flaws? This one blind spot might just be bigger than any of us thought.